All right, we're gonna pick back up with number 6. Needed to take a little bit of a break, but that's no problem. Let's go ahead and see what we're having what we're looking at right here. Okay, so it's another one involving trigonometric functions, and inside we have like a polynomial. Well, it's actually a rational function. So let's go ahead and let's just label them again. Our outer function here is going to be the cotangent function, and the derivative of the outer function is going to be minus cosecant squared of x. The inner function is going to be pi minus x to the minus 1, doing a quick little adjustment so I can more readily apply the power rule. Then the derivative of the inner function is going to be, careful here, the derivative of pi is 0, or just won't write it. Then we would have x to the minus 2. Okay, of course, x to the minus 2, you could also write this as 1 over x squared. So now that we have the setup out of the way, the derivative of y is going to be the outer function's derivative, so minus cosecant squared, and then instead of x, we'll just bring the inner function, pi minus 1 over x along, multiply it by the derivative of the inner, which is 1 over x squared. By the way, you could simplify this to a let's just keep it all blue, a minus cosecant squared of pi minus 1 over x. And then remember that this is all considered in the numerator over 1, so this x squared could be multiplied with that 1, and we end up with just this x squared in the denominator. Let's move that negative and just line things up to make it a little bit cleaner. So there is another derivative, this time involving trigonometric functions. So number 7 and 8, we've actually kind of seen this guy a little bit before, and we used the quotient rule to go ahead and figure out something like, we already did the derivative of e to the minus x by using the quotient rule, but you can see that it's just going to be e to the minus x times the derivative of the inner is minus 1. So again, we find that its derivative is minus e to the minus x. So maybe that's just a little callback to what we did earlier to have in your mind, but it would have been tedious to do the quotient rule kind of with this right here, because you would have had to also do the power rule to separate out the 5s and things like that. Just not feasible. So what we are going to do is just to apply the chain rule. And now that we've got the hang of it, I'm going to try to take off the training wheels a little bit. That is to say, I'm not going to really set up the inner and the outer from here on out, but I would still encourage you to do that if you need it. So the y prime is going to be the derivative of the outer. Actually, I take that back. This is a good one to do it because e to the x's derivative is itself. So actually, I'm not going to take the training wheels off yet. Let's just be safe. So the outer function here is going to be e to the x, because then, so let's keep it green. So that's going to be the outer function. Then the inner function is the minus 5x. So the outer is going to be e to the x, and its derivative, the d out, or derivative of outer, is itself. Then the inner is minus 5x, and then the derivative of the inner, or dn, is just going to be minus 5. So the derivative is going to be the e to the x, but not x. It's going to be just leaving the inside alone, then multiply it by the derivative of the inner, which is 5. So y prime here is equal to minus 5 e to the minus 5x. Looking at number 8 is similar, except for we have a little bit going on in there with the 2/3 x. Maybe just as a side note, you could rewrite this problem as e to the 2/3 x cubed, just to maybe make the constant multiple rule a little bit more obvious. Let's make sure I'm not getting too small there. That's okay. So what we have now is the outer function, again, is going to be this e, and then the inner function is the 2/3 x cubed. So the derivative of y is the outer function. So the outer is e to the x. Derivative of the outer is itself. So except for we're not going to put x there, we're going to put whatever the inner function is. And then we're going to multiply it by the derivative of the inner. So the inner is going to be 2/3 x cubed, and its derivative then is going to be 2/3 times 3x squared, or just 6. No, this 3's will cancel, so it's just 2x squared, because the 3's are going to cancel out. So then it's going to be 2x squared. So y prime, typically you'll see the constant multiples written first. So 2 followed by some sort of algebraic function, such as something that's just powering. So the x squared, the polynomial. And then we would have e to the 2 x squared over 3. I'm getting a little bit small in my writing here, so I'll go ahead and adjust that. Yeah, I'll just go ahead and adjust that like this. So resize, and that's better. And let's also do the same thing over here, just to make it a little bit easier to read later. Okay, so there are the kind of the basic forms of the chain rule. What we're going to look at next is kind of the scenario where it could be applied more than once, and in combination with other rules like the product rule and the quotient rule and things to that effect. So we have a series of examples with this one, and I'm going to kind of give you some help notating these, maybe just to break it up a little bit. So number 9 is going to involve finding the derivative with respect to t. So we're just adjusting our notation here a little bit. That's okay. So we have 3 functions involved right here. So I'm going to color code these as I rewrite the problem. So the derivative with respect to t, and I'm going to just go ahead and color code these and kind of mess with this square. So the square is the outermost function. So there's going to be the squaring function. And then there is going to be the sine function. And then the input to the sine function is going to be pi t minus 2. So I'm kind of going to drop the outer inner phrases a little bit. But I just want to kind of be able to get the hang of, okay, the outermost is going to be, write x if you're more comfortable with it, just to kind of get the pattern in your head. It's going to be the x squared, so it's going to be 2x. Then we're going to need also the derivative of the sine function is just going to be cosine of x. And then lastly, we're going to need the derivative of pi x minus 2. And again, I just chose x here because we're more comfortable with it. This one is using t as our variable. So that's just going to be pi. Again, because the derivative of pi x, think about pi is just 3, the derivative of 3x is 3, and the derivative of negative 2 is 0. So this is me just taking inventory of what I have to use, and now I'm just going to repeatedly apply the chain rule. So I'm going to take the derivative of the outer, which is going to be 2, and then I'm going to leave the inside alone. So the sine times, or not times, the sine of pi t minus 2. But now I need to multiply it by the derivative of sine, which is going to be cosine, but leaving, when I'm taking the derivative of sine of pi t minus 2, I take the derivative of the cosine, and I again leave the inside alone. And now I'm multiplied by the derivative of the inside, which is going to be pi. So it's quite a lot to look at, but when all is said and done, just kind of keep track of what we have. We have this pi and this 2 being multiplied. So we could actually bring this, so this is going to be 2 pi. Then we have times sine of pi t minus 2 times cosine of pi t minus 2. And maybe just to clean it up, just put a little multiplication symbol between those right there. But kind of keep in mind that these two right here act as the input to the trigonometric functions. So again, that's just a repeated application of the chain rule. 10 is very similar. I would encourage you to go ahead and try it, but here's an explanation. So just going to go ahead and do that same kind of separation of the square from the secant, realizing that the squaring function is the outermost function. Then we have the secant function, and its input is going to be pi t. So the derivatives I'll need, the derivative, I'm going to use t this time, of the t squared, or x squared, is 2t. The derivative of the secant function is going to be secant of x times tangent of x. And then the derivative, I should be consistent, these should be t's, not x's. I'm not switching my variable this time. So secant of t, tangent of t. And the derivative of, pi t is just, again, going to be pi. So with inventory taken care of, I'm going to go ahead and just apply the chain rule multiple times. So the 2 comes down in front. So that's the derivative of the outer. Leave the inside alone. Derivative times the derivative of the inner. So the derivative of secant is going to be secant times tangent. But remember to leave the inside alone. So pi t, pi t. And then lastly, multiply it by the derivative of the innermost, which is pi. So this is very similar to what we have above. But notice we have this secant and this secant, and technically this is 2 is just being multiplied by all of these terms. So this pi could come down out in front with this 2, and then we could combine these two secants. So this is ultimately going to be 2 pi secant squared of pi t. And notice we could combine these secants because they have the same inputs. And then they have tangent of pi t. Okay, so that is quite a bit to process. So make sure you're practicing. I'm going to go ahead and just look at maybe the hard form of the problems. I'm not going to necessarily do the whole thing. I just want to go ahead and kind of get you started to think about. Something to think about. Actually, I'll do this one. I was just looking at my notes. All right. So if you look at this, again, our variable this time is theta. We haven't dealt with theta as our variable too much, but it's good to be in the habit of it just to kind of give some variety. If this bothers you, you may just want to go ahead and just try it to get the hang of it as x times tangent of x to the 10th. But you can see when we do the derivative of the inner, we're going to also need to use the product rule. So that's why I always like to just take a moment off to the side and do inventory. So our outer function right here is going to be the power function, x to the 10 or theta to the 10. So just to get used to dealing with theta, I'm going to take the derivative of theta to the 10th, which is going to give times theta to the 9th. And then our inner function is going to be this theta times tangent of theta. So the derivative of theta times tangent of theta is equal to derivative of the second is a product rule. So the derivative of tangent is secant squared of theta times the second, which is tangent of theta, times the derivative of the first, which is 1. Oh, this should have been a plus right there. So quick little correction, that should have been a plus. Okay, so that's nice because I already have that taken care of off to the side. So now I could just use the chain rule. So the derivative here is going to be the derivative of the outer. So 10 times, leave the inside alone. So that is going to bring the theta times tangent of theta along. And then we are going to also need to multiply it by the derivative of the inner. So the inner its derivative has a sum, as we can see right there. So I'm going to just put parentheses, and then this is going to be theta times secant squared of theta plus tangent of theta. All right, so that was us using the product rule inside the chain rule. And another example right here in number 12. This time you have, again, the chain rule because this big rational function is the inner of this one. So if I'm just thinking about this e to the x is my outer, it's going to be e to the x, but the inner is going to be this rational function x squared over x cubed minus 4x. But then we have to multiply this by the derivative of the inner. So again, just instead of doing all the work right here, I'm just illustrating it. And I'm going to illustrate it by putting the little prime there saying I'm going to go ahead and need to do one more step. And that one more step is going to be just kind of this coming down, e to the x squared over x cubed minus 4x. But I'm going to have to actually go ahead and do the quotient rule there. So don't forget, you use your quotient rule. All right, and let's see, is that the majority of them? Yeah. So this chain rule allows us to go ahead and have some applications or be useful in some applications of working with other types of scenarios we've already encountered. One scenario would be in taking the derivative of the absolute value function. So if we had y equal to the absolute value of x, this is sometimes considered a non-algebraic function because it's not using your standard operation. It's defined piecewise, but it actually has an algebraic form, and that is to say you can rewrite this as the square root of x squared. If you think a moment why that's true, realize to square would get rid of any negatives in the input, and then you would bring it back down with a square root. We're not solving here, so you don't need plus or minus, but these are equivalent. But now you can go ahead and take the derivative of this using the chain rule, where the square root is acting as your outer function and x squared as your inner. So to go over that briefly, y prime would then be the outer, which would derivative would be 1 over 2 square root of x, but we're going to leave the inside alone, and then we're going to multiply it by 2x, the derivative of the inner. We can simplify this, the 2's cancel, and we end up with x over, well, realize that this is the same thing as this. So again, it's x over the absolute value of x. We've actually encountered this a little bit before. If you look back to section section 3.2 for the graph and discussion. The other thing we could also use the chain rule is to simplify or get rid of the need for the actual quotient rule. So I'll use this example right here to provide some context, but we can rewrite that given function as y times 1 minus 2x to the minus 3, just using basic properties of exponents to bring that out of the denominator. So now, again, we could use the chain rule. The derivative of the outer, so the minus 3, comes down in front, that's minus 4. Now leave the inside alone, which is 1 minus 2x, and multiply it by the derivative of the inside, which is 0 minus 2, or just minus 2. So this is ultimately going to give us y prime is going to give you 6 over 1 minus 2x to the 4th. So that was the derivative. It does ask us to go ahead and say and show that the slope of every tangent line to this curve is positive. Well, and that actually follows directly, and that's because this derivative is positive for all inputted x. The reason being is because the denominator is always positive, being an even powered function. So that's just a nice little context. But again, hopefully you're comfortable with the reasoning about why this is always positive, this is positive, and again, something at x to the 4th will always be positive, or I should at least say non-negative. And the fact that you couldn't, we'll just leave it at that. So yeah, this is positive. Or 0, but it wouldn't be, you wouldn't plug in 0 because then, or plug in something to get 0 because it wouldn't be defined in the original function to begin with. It has the same domain. Okay, so 15 is one other scenario where you'll see the view and examples. This is more of an FYI. You'll see the view and examples explained to do it using that first method we talked about. But if you get this set up, realize it might be worthwhile just to go ahead and say, okay, here's u and there's u, and u is this function right here. So just go ahead and do f of u, or of course this is just f of g of x, or you could finally do this as just, let's see, to the 5th power, plus 3, and then plug this in right here, the square root of x, which we're given above. Again, you could then use some properties of exponents. This is the square root, so this is x to the 5 halves plus 3. So it's a little easier to go ahead and take the derivative of this. So if you take the derivative of this and then plug in 1, it'll also give you the same answer. So just wanted to help you out with that. But that completes section, that completes section 3.6. In section 3.7, we talk about implicit differentiation, where the underpinning theory is that of the chain rule. Chain rule is one of those concepts that takes a while to get the hang of. So make sure you take your time and do lots of practice. And if you have questions, always feel free to reach out. Good luck.